Hey students, and welcome to today's video on the periodic table. We're now moving in to chapter 6. We've finished chapter 5 on electron configurations, and now we're going to be really focusing on this magical periodic table and all of the things that it can tell us about atoms and their behaviors and ions and elements and what all of those things are doing. And so we're going to be really spending a good chunk of time in this chapter starting to get a strong feeling for how the periodic table is organized and also how to use it to make chemistry a lot simpler and a lot more straightforward. We're going to use this kind of little cheat sheet of the periodic table to our advantage instead of memorizing a lot of disconnected facts. We're going to start this with just a little look back at the first periodic table. So this good looking guy right here, Dmitri Mendeleev, was the father of the periodic table. He took a list of 60 elements that had been debated and agreed upon by a group of chemists. And Dmitri Mendeleev came home from the International Meeting of Chemists and brought with him this list of elements, and there was no real arrangement for them. So what he did is he saw that if he arranged them according to their average atomic mass, they lined up so that elements in the same column had similar properties. So he started, and he didn't have all of these elements, but he took 60 elements and he arranged them. And so if he arranged them by increasing average atomic mass, they were going to keep everything in the same column with a similar property that could be described and predicted. The really cool part about this is Mendeleev left some spaces in the periodic table for elements that he predicted would exist but had not been discovered yet, and those were later discovered. He also had to make an exception. This is the iodine-tellurium exception. So if you look at iodine and tellurium, they are over here in group 16 and 17 of the periodic table. And iodine, although its atomic number is 53, has a lighter atomic mass, and tellurium has a heavier atomic mass. And what Mendeleev noticed was that iodine and tellurium should switch places. So even though he had made his list by increasing average atomic mass, he noticed that the properties of tellurium fit more in its group with oxygen, and the properties of iodine fit more in its group with fluorine. And so he made that switch. And that kind of really big picture thinking is why we call Mendeleev the father of the periodic table, even though the periodic table that we use today was completed by someone else. So Mendeleev had the idea for the periodic table, and he created a periodic table using average atomic mass. But it was Moseley that finished the table, and it was Moseley's updates that create the table that we have today. So this periodic table was finally made in 1911. Moseley rearranged the data, rearranged the elements, and he decided to arrange according to atomic number instead of according to atomic mass. And what that did was it fixed the iodine-tellurium problem so that iodine fit in group 17 with fluorine as it should, and tellurium fit in group 16 with oxygen as it should. And so he sort of solved that one problem that Mendeleev had to sidestep. Moseley's table is the basis for the periodic table, the one that you have in your book, in your notes, online, all over. This is the most commonly used periodic table, is the one that was born from Mendeleev, but then finally finished up by Moseley. And even since then, some groups and families have been added to the periodic table. Like at the time, they didn't even know about the F block down here, but now we do. At the time, they didn't even know about the noble gases over here, but now we do. So since then, we've made some advancements, but they've all fit within our periodic table, which really shows you that your system is working if even brand new discoveries can fit in the table that you have created. So it was really good. It's a really nice table, and we're really focusing on how to use it, because it's one thing to say the periodic table is great, and it's another thing to be able to use the periodic table to make your life easier. So if we look together at the periodic table, what you're going to see is that groups 1 and 2 and 13 through 18 are called the main groups. And so I'm just rattling off these little numbers now. What I want you to do is look at your periodic table, either the one you printed or the one from the back of your book, or Google periodic table right now, and notice that above each of the columns, there is a number 1 through 18. So there are 18 columns in the periodic table. If we start with hydrogen over here, and then beryllium, that's 2, and then scandium through zinc is 3 through 12, and then we jump back up for boron is 13, and then through to helium is 18. So we have all of these different groups. So groups 1 and 2 and 13 through 18 together are known as the main groups. And if you're looking at the periodic table that's here, you should be noticing that if we do groups 1 and 2 and 13 through 18, I'm really discussing the S block and the P block. We have already learned that. And so this is also where we finally learn about the blocks on the periodic table according to your textbook. So the table, we saw this table last chapter, and it has the S, the P, the D, and the F blocks colored in and labeled with their principal energy levels and everything. This is the one we used for electron configurations. So the periodic table can tell us what group something is in. A group or a family is where we can predict, or how we can predict an atom will behave. It behaves similar to other elements in its group or family. And then we can also look at the different blocks of the periodic table, and those represent what orbital is filling in that atom's electron cloud. And so based on their location, we can know what the electrons, how the electrons are filling up, and also how the atom might behave because of its position. So there's something I want to tell you right up front, and that is that the noble gases, this column 18, the noble gases are the goal. They have 8 electrons in their valence shell, and every atom on the periodic table wants an electron configuration that is similar to one of those noble gases. And so that group of noble gases in group 18, they have the valence shell that everybody wants. The valence shell is the outermost electrons of the atom. So when we look at the drawing of an atom, if we're going to look at sodium, this is what we'll find. So this is a standard model for what sodium looks like. The rules of thumb when drawing an atom is that we start, our innermost shell has 2 electrons here. That's n equals 1, or that 1s orbital, it can only have 2 electrons. And then as we continue across the periodic table, we're going to go across the periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Those are the 6 electrons that are in our next ring. And then finally, in my outermost ring, I have sodium with its 1 more electron to give me a total of 11 electrons in this shell. This out here is called the valence shell. And this outermost valence shell is the same for all of the elements in a particular group. It explains the behavior of the atom both in bonds and in ions. And we'll spend some more time talking about this, but the valence shell are the highest principal energy levels of the atom. The highest PQN, or the highest principal quantum number. So if this is n equals 1 down here, and this is n equals 2, then this is n equals 3, and this highest principal quantum number represents my valence shell. Let's just look at what sodium's electron configuration looks like and compare it to this drawing. This is sodium's electron configuration: 1s2, 2s2, 2p6, 3s1. And I just want to connect these two things for a moment. 1s2 represents this innermost shell and these 1, 2 electrons. 2s2 and 2p6 gives me a grand total of 8 electrons in the next shell. And those are represented here. 1, 2, 3, 4, 5, 6, 7, 8. So that's 10 electrons. And one more with my highest energy level. This one is my valence shell. With my highest principal quantum number, I can recognize that there's one electron in my valence shell, both from looking at the highest principal quantum number of my electron configuration and by looking at the outermost ring of electrons on my Bohr model. So both of these things help me to know the outermost group. An atom is the most stable if its valence shell is full, a full octet, a stable valence shell. That's what atoms are after, and that's what the noble gases have. So everything in group 18 has a full valence shell. So we say that elements in group 18, the noble gases, have a full valence shell. They have a stable octet, and this makes them very unreactive. We're going to come back to all of these features, but what it's important to know is that when an atom is close to being able to become like a noble gas, they are really willing to do it, okay? A noble gas is like the perfect low energy place for an atom to be, to have its valence shell like the noble gas. And so atoms will beg, borrow, and steal in order to become like a noble gas so that they can relax. So the closer an element is to becoming like a noble gas, the more reactive it is. This is a trend that you're going to see throughout this chapter.